Oh, here we go. So it's Tuesday, it's the second, we're doing improper integrals. And let's do one. Okay, let's start with an easy one. Here it is. Okay, it goes like this. What's the definite integral, like an area problem, right? From 0 to 1 of 1 over x dx. Now tell me, why is this improper? What's improper about it? There's something bad. Do you see it? I don't know.
Wouldn't that just be the same as 1 over x dx?
1 over x dx, ln, yeah, that's not bad. What?
ln 0, you can't have it. Sorry.
ln what? No, she's right, the antiderivative is ln, but that's not the problem. What?
I'm changing my answer to Kansas student.
That's not a legal answer. Okay, next.
ln of 0, but you can't have it.
ln of 0, that's a problem. Yeah, that's a problem. Okay, the 0 is the problem. Yeah, the 0 is a problem. Not only is ln of 0 undefined, but 1 over 0 is undefined. The integrand is undefined even. Okay? So there are three classes of improper integrals. I give them three different names. I call them A, B, or C. All right? Now remember in the fundamental theorem of calculus, we say the integral from A to B of cap f of x, blah, 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 right? That stuff? Okay, well, what's the problem here? Is it A, is it B, or is it something in between? A. So what you do is you treat it as a limit. You rewrite it as a limit as A goes to 0 from the right. Of the same thing, but now it's A down here. Why is that good? Well, because the idea is 0, you can't plug it in to the integrand. You can't plug it into the antiderivative either. But maybe you can accumulate the area from, say, 1 to 0.1, 1 to 0.01, 1 to 0.001, and you might have a convergence, which means that the area is bounded. The area exists, even though you can't plug in 0. So when we have an improper integral, we do it as a limit. Now let's do that. The limit as a goes to 0 of what? Well, what is the antiderivative again? ln, right? So ln absolute x evaluated from a to 1. All right, so do what you usually do. Don't do this yet. This is last. Do what you usually do here. What? Plug in what? ln of 1 minus ln of a. Absolute a. The absolute value really doesn't matter because it's bigger than 0, right? It's not negative, but whatever. And we're going to evaluate this as a goes to 0. Well, what's ln of 1? No. 0, right? Remember ln of 1 is 0. Remember ln looks like this. It goes through 1, 0, right? It goes to negative infinity, goes to positive infinity, has a vertical asymptote, it goes through 1, 0. Okay. So that's fine. That's 0. But what about this? As a approaches 0, what does ln a do? As x approaches 0, what does ln x do? Goes to negative infinity. So what's 0 minus a negative infinity? Just positive infinity. By the way, we really shouldn't write this because a limit and an integral, a definite integral, is a number. This is not. Among friends, that's what it's doing. But the answer is this. What did I write? What did I mean? Divergent. Or you could write this, I guess. Right? This is really not an answer. I wouldn't do this on the AP. They might get a little upset with you. But everyone does this among friends. I mean, yeah. Okay? The idea is that this limit grows without bounds as a positive number. That's what that means. But the answer is divergent or does not exist or whatever. Okay? Now, that doesn't mean that improper integrals always diverge, though. Some improper integrals actually do have a limit. So let's play around with this a little bit. All right, let's try this again. Now I'm going to do the integral from 1 to infinity of 1 over x dx. Now who's bad, A, B, or C? B is not a number. That's bad. But we can still rewrite it as a limit. The limit, if the problem is B, I usually say B here, right? As B approaches positive infinity, the positive is optional. I always write it, I don't know why. The integral from 1 to B of the same integrand. This is really the same question almost. Different region, different area, but the same curve. All right, so the problem could be at A, it could be at B, or it could be somewhere in between. This is a B improper integral, right? So what do? The limit as B approaches positive infinity of what now? What should I write? ln absolute x evaluated from 1 to b. Okay, so first you plug in b, then you minus what? ln absolute 1. Well, ln of 1 is still 0. And what does ln b do as b goes huge? What does ln x do as x goes huge? As x gets huge, y goes positive. It goes as big as you want. It doesn't blow up too very fast, but it blows up. Okay, so again, I could say positive infinity, or I could say this diverges, or I could say it does not exist. All right, we just saw two improper integrals, an A class and a B class, that do not exist. Does that mean all improper integrals do not exist? No. Let's try some more. Let's see if we can find some that work. As long as they can tell what it is, I don't think so. If it's that ugly that you can't tell what it is, well, that's a problem. Okay, how about this? All right, so what is this? A, B, or C? This is improper. A, what's wrong with A? Zero's okay, plug it in. What's wrong with 0? B is okay. C, yeah, what's C? I didn't say you were wrong. What's bad? What C value is bad? C meaning between 0 and 3. What's bad? 2, sure, it's undefined at 2, isn't it? The integrand anyway. No, leave her out of this. Okay, so now what? You're forgetting I'm Cuban. And my parents are Spanish from Spain. What?
But you speak like every language anyway, so we could try.
Yeah.
Wait, you're German? Wait, you speak German? English?
I'm rusty on my German, but.
You know what he can say is...
No, this guy on WoW, I play WoW, right? This guy on WoW, he knows I speak German, so he insists on talking in German. Whenever we're doing, playing together, so he's always writing in German. It's like, oh, so I got to figure out. Then I got so tired of it. You know, Babelfish? You know Babelfish? No? I sort of cheat and go into Babelfish and write down what I want in English and click translate and then just copy and paste. No, because, I don't remember a lot of my German, so I'm a little rusty. But anyway, we digress. Now, so the problem is the 2. So what does that mean? What are you going to do with this? Wait, one person talks. I can't hear two people. Steve, what? 2 integrals. Break it up. Yeah. Okay. That sounds good. Okay. So this is going to be the limit as C approaches 1 from the left, the integral from 0 to C of that same integrand. Plus, what should I continue with? No. The limit as C approaches 1 from the right, because I'm going from C to 3. If you were actually doing this on... It's 2, isn't it? Oh, I know what I did. Sorry, I copied my notes wrong.
Are you serious?
Yeah. Whoops, I can't see my notes. It was a 1, sorry. But, yeah, everything was said was still valid. Relax. It's just 1. It'll work for 2, too, Okay, now, yeah, snafu, watch out. Okay, so why is it from the left? Why is it from the right? What's that about? Well, yeah, but see, if you were actually doing a convergence table, you'd be trying to go from 0 to as close to 1 as possible. You can't plug in 1, right? So you can plug in 0.9, 0.99, 0.999, 0.99999, see if you get a convergence. Same thing here. You can't do from 1 to 3 because you can't plug in 1, but you could do from, I don't know, 2.9 to, 1. Yeah, 1.01. Yeah, 1.1 to 3. 1.0001 to 3. 1.0001 to, right? You get the idea. So we could do this on HAL, make a convergence table out of it, see if this limit exists, see if this limit exists, and add them up. By the way, what if this one blows up and this one doesn't? It still doesn't exist. So like 2 plus infinity is bad, right? So they both have to exist for the whole thing to exist, right? Okay, so now, how do you anti-differentiate it? It's a U sub, yeah, who's U? X minus 1. So who's du? 1 dx. So if that's u, that's du. Does that help? Don't say ln. I know some of you are thinking ln. Yeah, it's this. It's a power rule. If u is this, this is du. So how do you do u to the n du? Add 1 and divide by the same thing. So u to the negative 2/3 plus 1. What's negative 2/3 plus 1? 1/3. And if you divide by 1/3, you're really multiplying by 3, right? Okay, so it's the limit as c approaches 1 from the left of, okay, it was 3 times this to the 1/3, right? 3 times this to the 1/3, or the cube root if you want to write a cube root, from 0 to c, plus the limit as c approaches 1 from the right of the same antiderivative with these limits of integration. Okay, if you like to write cube roots, more power to you. All right, so what do you do next? Fundamental theorem of calculus part 1 says plug in. Who? No, plug in first. You did it in the last question. I asked the same question. Plug in what first? C, then plug in 0 and subtract in that order. Okay, so the limit as c approaches 1 from the left of 3 times c minus 1 to the 1/3 minus 3 times 0 minus 1 to the 1/3. This whole thing is being modified by this limit operator. Plus the limit as c approaches 1 from the right of, what should I write? 3 times 3 minus 1 to the 1/3 minus 3 times c minus 1 to the 1/3. And this limit operator is modifying all of this. Alrighty then. So let's do it. Well, let's see. Can you plug in 1? Is that a plug-in limit? Is that okay? If you plug in 1, what happens? 1 minus 1, positive exponents in the numerator, that's legal. 0 times 3, 0. Okay, so that zeroes out. What's 1 minus 0 minus 1? 0 minus 1? Negative 1. What's negative 1 to the cube root? It's still negative 1. So and times a negative 3 is a positive 3. So I got 0 plus 3 is 3. Okay, so this branch exists. Remember, this limit has to exist and this limit has to exist, right? Plus, okay, what do we got over here? Well, 3 minus 1, 2. So I got the cube root of 2 times 3. You could write it like this if you want. Cube root of 2, right? Minus what? If I plug in 1, is that okay? Is it a plug-in limit? Plug in 1? Sure, 1 minus 1? 0. 0 to the 1/3? 0 times 3? 0. So 3 cube root of 2 minus 0. Fine, done. So this limit exists, this limit exists, so this limit exists. This is a limit. Okay? So yeah, sometimes the improper integrals converge. All right, so let's ask Cal about all this stuff. How would you do this on Hal and get a convergence table out of it? Okay? Let's go back to the first question and see why it diverges. Okay? Can I move backward? Are you done with this? Okay, I'm moving backward. Ready? See a lot of writing going on. Legal? Safe? Okay. All right, let's go back to the very beginning, this one. How would you do this on the calculator? You'd have to plug in limits from 0.1 to 1, 0.01 to 1, 0.001 to 1, and see what happens. Like what? Well, no, that's it. You would either do it numerically like that or do what we did analytically. All right, so let's ask Hal. Okay, Hal. Yeah, by the way, this is sort of annoying that in my third period I have to switch to an 83. Ugh. Well, they don't. It's Ziggy. Yeah. No, it's Ziggy, and they don't like my nicknames. I don't know. Whatever. Yeah. Yeah. You will like my nickname, damn it. All right. So second, the name is Ziggy, and you will like it. Okay. 1 divided by x, comma x. And of course, that's ln. I don't have to check that, right? From 0.1 to 1. Okay. What do you get? Okay, fine. Now remember, we got divergent, didn't we? Why? Well, look at this convergence table. It's not. It's a divergence table. What if I get closer to 0? Look what it did. It basically doubled, right? So predict the next one. What do you think? If use the same pattern. 9.2? All right. Let's see. Whoops. Not really. It's not doubling. What's it doing? It's actually adding. It's 2.3 plus 2.3 plus 2.3. Now it should be the 9.2, no? If I do it again? So this is getting predictably larger and larger and larger. It's not getting closer and closer to anything. I can make it as big as I want. I can make it more than 10, more than 100, more than 1,000, more than a million, more than a billion. I can make it infinite if I want. So this diverges. That's a divergence table. Okay, if you wrote that down in table form, right? Okay, likewise with this one. This one, you go from 1 to 1, 1 to 10, 1 to 100, 1 to 1,000, right? All right. So, whoops. Where am I going? Okay, get back over here, Hal. So this one is starting at 1 and getting bigger, right? So we'll start with a 1. And 1 to 1 is clearly what? 0, right? Because there's no area between 1 and 1. Okay, but that's not really what I want. I want 1 to 10. Well, I want a decimal. Yeah, that's not very helpful. Yeah, and that takes all day. Why are you taking all day, you stupid thing? You know what? I think I could do this. If I plug in a decimal, I'm going to get decimals out, I think. Yeah. Okay, that's an overloaded operator, right, Steve? Okay, so, you know what I'm talking about, right? If I plug in ints, I get exact answers. If I plug in doubles, okay. All right, so, boom. Oh, guess what? It looks like it's doing the same thing. It's doing the exact same thing. So that's why it diverges. Right, as B gets larger and larger and larger, right? So that's a divergence table. How about this one? Can we confirm that this is a convergence? Let's do this and show that we get 3. Let's do this and show that we get 3 cube root of 2. All right, so we'll do this one separate. So 0 to closer and closer to 1. Okay. So now it's second 7 of 1 divided by the quantity x minus 1 to the 2/3. I got to put that in parentheses or it'll just square, right?
Oh, no.
From x. And wait, let's just check our antiderivative. Is that what we said?
Yes.
That's what we said. Oh, we're so good at this. Okay, so we're going to go from 0 to what? Want to get closer and closer to 1 from the left, so 0.9. Okay, let's see what you get here. Oh. What the freak are you doing, Hal? Well, Hal is evil. Remember, don't forget, Hal is evil. White? But is it, though, from 0 to 1? If you plug in 0, it isn't, though. It's allowing, it's doing the principal root in DeMarva's theorem. Oh, schnooks. All right, is there a way to get out of this? Let's see, wait, mode, let's see.
Wait, did this happen first period?
No, because I didn't ask this question. I don't do the same thing every period. It's boring.
Because we're the more fun period.
See? Ha ha. Okay, look. Hal is evil because Hal knows how to deal with cube roots that are not necessarily real. If you have the cube root of something, there are really 3 answers. If one of them is real, 2 of them are complex. And Hal gave me a complex answer. To avoid that, I changed the mode for complex format to stick to real. Okay, Hal? Yeah, there are 3 roots. Yeah, I want the principal or real root, so that's okay. Now, Ethan was saying, I got I, and I ignored him, so anyway. Because I didn't ask that question. Anyway, so now I'm getting closer and closer to 1, and then the B is getting closer and closer to 1. What's the limit doing? Is it converging to something?
Yes.
Is it approaching 3 like we wanted it to from below? Yes, it is. Oh, let's cut to the chase already. I can get it as close to 3 as I want. Damn it. Okay. Wow, this is a big convergence table. If you have to write all these down. Well, you get the idea. It's getting closer and closer to 3, right? 2.9 repeating is 3, remember? Okay, and you could do the same thing over here. All right, so anyway, you could confirm all of these numerically. Here's another example. You ready for another one, a new one? All right, we're good at this. All right, consider the following curve. I don't know if you remember this one. I think we did one like this before. All right, let's say I gave you the curve y equals e to the negative x. So exponential decay, right? And so it goes through 1, doesn't it, if you plug in 0? E to the 0? Okay. What if I want to take vertical strips in dx, and I revolve them around the x-axis, so I want a volume of revolution. What type is this, disk, washer, or shell? If I take this strip and revolve it around the x-axis, am I getting disk, washer, or shell? Disk. I want the area bounded by this curve, the volume, bounded by this curve from 0 to wherever they meet, do they? Does e to the negative x ever hit the x-axis? No, so from 0 to what? Infinity. All right, so set up this volume of revolution about the x-axis. Vx is what? How do you do disks? This was Gabriel's horn, remember this one? We did do this, I think. All right, so how do you set up a disk problem? Pi r squared. Who's the r? Who's the radius of rotation? It's the y value, right? Okay. Times? No, height. That is the height, basically. The width, the thickness, right. Okay. All right, so if I call that dv, the volume of just one slice, that's my Riemann statement. Remember this stuff? Now, remember on the AP, very often they give you some weird verbiage. They say, set up an integral of a single real variable. What are they talking about? They don't want to see y's and x's, right? But who's y? E to the negative x. And how do you square e to the negative x? E to the negative 2x. So that's what I'm going to write. Okay. E to the negative 2x. Now, how do you convert this to an integral that represents the entire volume from x equals 0 on? I want the entire volume. So how do you change it? From 0 to infinity. There you go. So is this an A, a B, or a C case for improper integrals? Who's bad, A, B, or C? B. This is a B case. Okay, good. So rewrite it as a limit in B, right? Okay, so let's do it. Equals pi times the limit as B goes to positive infinity. The integral from 0 to B, e to the negative 2x dx. Didn't we do this, something like this some time ago? I think we did it with arc length or something. We're talking about Gabriel's horn. This is Gabriel's horn problem, right? Yeah. So this is the volume of Gabriel's horn. And the horn is infinitely long, but can you blow it? It doesn't have finite air column inside, right? Well, he's Archangel Gabriel, he can handle this. It's okay. Okay? All right, so now what? So how do you integrate this? What technique of integration would you apply? U sub, right. Who's you? Who's you? Negative 2x. So who's du? Negative 2 dx. So replace dx with du over negative 2, right. Okay. So you're going to have pi times the limit as b goes to infinity of negative 1/2 du instead of dx, right? So it's a negative 1/2 e to the u du. How do you integrate e to the u du? It's e to the u. So it's negative 1/2 e to the u. But u is negative 2x, isn't it? And we're evaluating this from 0 to b. All right. So let's do it. Pi times the limit. As b gets huge, plug in b, so negative e to the negative 2b over 2. Minus is plus e to the, 0 over 2. Of course, e to the 0 is what? 1. And what's this limit? As b gets humongous, what does e to the negative 2b do? Approaches 0. Because what is e to the negative 2b really? It's 1 over e to the 2b. I could write it this way. 1 over 2 e to the 2b. So e to the 2b gets huge as b gets huge, and this is 1 over humongous is basically going to 0. So this limit is what? 1/2 times pi is pi over 2. All right? So pi over 2 is about 1.57 something, so that volume is finite. If the units started out in inches, that's in cubic inches, let's say. All right? Okay, let's try another one. You ready? Let's see how you do with this one. Okay, shall I move on? We are moving on. Boom. Okay. The integral from 0 to 1 of 1 over rad 1 minus x squared times 1 plus x. Okay, who's the culprit now, A, B, or C? A is okay, you can plug in 0. C, no, C's not the problem. It's B, it's 1. Right? You can't plug in 1 in the integrand, can you? And probably in the antiderivative too. Okay, so that's the first question. How do you rewrite it? As the limit for b goes to 1, the integral from 0 to 1 b, as we approach from the left. Okay, now the question is, can you anti-differentiate this thing? How do you anti-differentiate that thing? The thing. You could do partial fractions, but that's too complicated. You could do trig sub, but that's too complicated. They both work, but there's an easier way. You could break this up as 2 fractions already without doing partial fractions. Do you see it? It's like 2 integrals. Couldn't you rewrite that fraction as a sum of 2 fractions with the same denominator? What's nice about this is you end up with stuff you know how to integrate. So let's write that. It's a limit as b approaches 1 from the left of the integral from 0 to b of 1 over this dx plus the integral from 0 to b of x over this dx. I could break it up as 2 separate integrals. It's 2 separate fractions. I don't have to do this. I could just say this, I guess. Okay? Now, how do you integrate 1 over 1 plus x squared dx? You know this one. You should know this one. We derived this one already. Nobody remembers. Arc, yeah, arc. No? Arc, sine. Arctan had a plus and no radical. Arc sine is this. 1 over rad 1 plus 1 minus u squared du? Okay. So this is the limit as b goes to 1 from the left of the arc sine of x evaluated from 0 to b. Okay. What about this one? How do you integrate this one? I'll give you a hint. Power rule thing. Who's u? 1 minus x squared. So who's du? Negative 2x dx. So replace x dx with negative 1/2 of du. Right. Right? Okay, so it's going to be plus, minus. Okay, minus stuff over 2. Now what is it? It's u to the n du. How do you integrate u to the n du? How do you integrate u to the n du? I got negative 1/2 u to the n du. What do you do with n? Add 1, add 1. So it becomes a half, and you're dividing by half, so times 2. So the other 2, they're gone, so forget that. And it ends up to the 1/2. That's all that's left. All right, so plug in b. The limit as b approaches 1 from the left of the arc sine of b minus rad 1 minus b squared minus, plug in 0, the arc sine of 0 minus rad 1 minus 0 squared, all modified by this limit operator here. So can you just plug in 1? What's the arc sine of 1? What's the angle whose sine is 1? 90 degrees. We're doing radians here. Pi over 2, right. What if we plug in 1 here? If you plug in 1 here, what happens? 0, right. What's the angle whose sine is 0? It's 0. It goes, sine curve goes through 0, 0, doesn't it? And what's 1 minus 0? What's rad 1? So I'm subtracting 1, but I was subtracting already. So plus 1. Ta-da! And that's all she wrote. Who gets the notes? That's it. There you go. She gets some smartboard notes from the first period. Okay, so I'm done. Bye.